So welcome everybody, and welcome to this short introduction to some key programming elements which are useful for the optimization of your codes. So some of the things are things which you may have heard of before, like vectorization, but not everybody is familiar with that. So I wanted to say something about that first, and then about how we parallelize with MPI and OpenMP. And the parallelization, as we mentioned last week, is a pretty trivial thing in the sense that we can split all the tasks and send them to different processes. And then there will be one main process, which at the end of the calculations collects the data from all the previous processes. So let's take a look at some of these technicalities. So these slides contain perhaps a little bit more than what we will have time to cover. But one of the things are simply about the compiler options, also tools to benchmark your codes, which we discussed partly last week. And then we want to say something a little bit about vectorization, which is pretty useful to have a deeper understanding of. So let me ask you guys, have you heard of vectorization before of your codes? No, one of you. Okay. So if it's okay, I will just say a little bit about it, because this is something you can get for free. Now, the problem in Python is that with just-in-time compilations, etc., some of these things actually hid behind a wall for us. So sometimes it's difficult to actually fully understand how you can improve a Python code. Whereas in C++, which is a low-level language, it doesn't mean that it's a low-quality language, but we say it's a low-level language in the sense that it's much closer to machine instructions. And it's an extremely rich language, as you know. Many of the same things which you see here for C++ apply to Fortran programming as well, to Java programming. So one of the things we discussed quickly last time was actually the type of compiler options and the kind of strategies which you would use when you compile and develop your code. So if you don't do anything, the compiling and linking with libraries gives you a code where you essentially translate line by line what you have told the program to do. So that means that with this optimization, now with this compilation and linking flags, you're not trying to optimize your code. So it's essentially you translating what you have written line by line into assembly code and machine language. So this is often called a flat compiler option. The thing here is that when you are developing your program, this is something which is extremely useful, because then you know that the compiler is supposed to do roughly what you tell it to do. So if you're sure that your algorithm is implemented correctly, this is a very useful test of your codes. So when you then include compiler flag, where the compiler tries to optimize your code, because there are optimizations which it can do, then you have to be sure that you get the same result as you did when you implemented the algorithm in its brute force way. Because sometimes there can be error when you include an optimization flag. Yeah. So when you use no optimization flags, that means essentially that you translate your code into machine language as you have written the code. There is a manual here which is very useful, and these are the typical flags which you will end up using, and it depends also on the type of compiler you have. If you go to the supercomputers, which you may have access to, then there can be different types of compilers you can invoke. In general, this is just the GNU library C++ compiler, which comes by default. But different operating systems can have their native C++ compilers. So if you work on a Mac, it's called CLang, which is a slightly different compiler. As we also mentioned last time, I'm just repeating some of the things. there is a possibility of using profiling options. So this is something you would do when you test your program. You would not use that when you run your program, because this option PG will slow down your program because it counts all the time you call a function. So you get an additional overhead in the run of your code. So this is something you would do in the development stage, as we say here. And this allows you, when you run it with a profiling code, the output here tells you which functions are being called the most. So if you find that the function uses 70% of the time, that is where you would invest your thinking on making the program run faster. And if you have some by accident, and this happens, you can have some multiplications in the inner part of a loop, and that can slow down your code. There can be an inefficient allocation of memory that can also slow down your code. So when you look at this profiling function, and if a function is flagged as a function which uses most of your CPU cycles, that's where you should put in your efforts in trying to speed up your program. So this kind of profiling is extremely useful. And one of the reasons why we always recommend people to have short functions is that if your function is 200, 300 lines, it's much more difficult to figure out where can I optimize it. If it's something between 30 to 50 lines, which is a kind of optimal length, or what you should try to keep your functions within, then it's easier to figure out where can I find the bottlenecks. So I wanted to go through some small tips and hints on how you can optimize your program before you call these compilation flags. And there are actually many tools. And if you're familiar with some tools which I don't mention here, just send me a message and I will update my notes here. There are also debugging options where you can step through your program. There are in the development environments, so-called IDEs, like Qt Creator, which is just great when it comes to finding out how the program is progressing, if you have memory leaks, etc. Some of you probably use Atom as a text editor and also an editor to develop code. That is also a very powerful way to actually make many of these tests when you run your programs. So some of the compiler flags are specific for specific operating system. So you should always, if you go back, look at this man file, C++. This is under Unix, Linux. So if you're on a OS X system, always open a terminal and then you can run these commands in terminal mode. If you are on a Windows operating system, you would have compilers like Visual Studio, which also have many of these help functions. I am less familiar with that because I don't have a Windows machine. So I would not be able to give you proper advice there because it's 10, 15 years since I used it. Last time we mentioned quickly some hints. So one of the things which a compiler flag would try to do for you. So the compiler tries to figure out whether it can optimize it. But the compiler is not a super genius, obviously. So it does only simple things. And sometimes it can do simple things in the wrong way. So that's why you should always compare with no compiler flags. So if you have no compiler flag on this function here, it just translates what you have into machine code. And as we discussed last time, if you then perform millions of multiplications, you would just waste millions of cycles here on a multiplication of two constants, C and D. So this is a typical example of a function which is badly written and where we simply have coded the mathematics as it stands. So this applies also to if you guys use MATLAB or if you use Mathematica or symbolic Python to get an analytical expression for a function or derivative or whatever. And then like SymPy and Mathematica and MATLAB, they allow you to translate this into C++ code or Python code, but then it would take an expression without thinking of simplifications. So if you are doing polynomial multiplications, it will often just write a code which is highly inefficient for you. So just keep in mind that this would typically be the way you would write the mathematics. And if you look at the last statement before the end of the loop, you have a memory lookup. And this E, this constant K, is just a constant, and it doesn't depend on the loop. So if you have a 1 million loop variables here, you're doing 1 million memory lookups. So one thing which is difficult to quantify properly when it comes to time is the number of memory lookups and the number of memory writes. So this is an example of, if you look at the code here, you have one memory lookup and one memory write. So that's an operation which typically is not counted when you look at the number of floating point operations in an algorithm. So the number of floating point operations here would be one multiplication and one addition. So if you do this 1 million times, you have 2 million floating point operations. If you then can write this in terms of a constant here, you have reduced 2 million floating point operations to just 1 million floating point operations. So even if the mathematics looks nice, like this is the way you would write it, this is highly inefficient. So give that a thought when you write your programs, because it's very easy to have a mathematical expression and then simply code that one. And in particular, if this is inside a loop, if you have 2 to 3 nested loops and you have that inside, then that's going to be, you're going to pay a high price for that. And when we run Monte Carlo calculations, we're actually running millions of over millions of cycles. So again, this is also a typical case where you would then have, with n equal to 1 million, you would have 1 million memory lookups, which are just totally wasted. And a memory lookup is actually you, it's not as you going down into your basement and picking some food or whatever. So that would be a kind of memory lookup. You go into your fridge, if you think of that as your memory, and you pick an item. So a memory lookup is a physical operation where you actually have to go to memory place because it points to a specific slot and fetch that variable. So that is also something which can slow down performance. So think about all these things when you write the program, because Monte Carlo calculations are data greedy, as we said, which means that you're going to run as many Monte Carlo cycles as you can. And if you can then speed up some of the processes, you should think of doing that. There, in a typical Monte Carlo calculation, there is not much memory lookups and memory writes. So that makes life easier for us if, in that sense. But we will typically have lots of floating point operations. So the basic idea of vectorization, if you think of the present CPUs which you have on the market, so I'm not discussing GPUs now, they are already including quite some level of parallelism. So vectorization is normally included, and this is something which has been around for more than 20 years. It came already in the 90s in standard CPUs for laptops and PCs. And you would typically have a situation where you have multiple processors which are involved to solve a global problem. So this laptop here has actually 16 cores. So it's almost a kind of standard. So I can run 16 threads in parallel if I want to. So if you look at hardware, the first one is basically outdated. Single instruction, multiple data. They contain much of the ideas of parallelization. And modern laptops, even your laptops, they are typically multiple instruction, multiple data. This is the kind of basic structure which you have. Now, one thing which is important for us is actually to to think of the type of memory which we want to use and which we need. So a Monte Carlo calculation is not, the way we are setting it up, is not memory intensive. We don't need to allocate much memory. This means that we can typically run everything in most applications with what's called a shared memory. So shared memory, if you're not too familiar with that concept, that is the memory you would have on a specific unit. So my laptop has, what is it now, 32 gigabytes of random access memory, roughly. I think it's 16 or 32, I don't remember exactly. And if you look at many of the farms which you have in high performance computing facilities, this is a farm of PCs, which means that you will have a shared memory for every PC, and every PC can run, let's say, 16, 32, 64 processes in parallel. And then you would have distributed memory, so you can actually access more memory. So a typical high performance computing facility has a farm of PCs where every PC has between typically 8 to something like 64 or higher powers of 228 cores. And then you can access up to typically 1 terabyte to 2 terabyte of memory. That's a typical PC on a high performance computing cluster. So if you have hundreds of these, suppose 100, then you can actually access 200 terabytes of memory, but that will be distributed memory. So that means that when you run a process with distributed memory, like if you're solving partial differential equations, then it's pretty common that you would split your integration grid in smaller blocks. And then every process or every unit would then run with its own part of your integration grid. And that means that you can distribute the memory across many, many units. So when I say a unit, I'm thinking of a PC in one of these high performance computing farms. And then we are connecting these in parallel. So that means that we are dealing with a distributed memory setup. And that's the most typical setup for most of the high performance computing facilities. So just a farm of different PCs. And in our case, we will often just be happy with a shared memory. The way we are going to set up a Monte Carlo parallel calculation is simply, as I said, there will be a main process which decides what kind of, how many processes are participating. And then with that, you would distribute the job. And every process has a copy of your program and runs that independently. And then at the end, this main process collects all the results from the sub processes, and then sums up the results, and then produces a final output for you. So this would be the typical way you would run a Monte Carlo calculation. And you will see that often being referenced as embarrassingly trivial to parallelize. So if you're solving differential equations, on the other hand, there are even special functions, if you're using MPI, which are tailored to specific types of partial differential equations, so that you can distribute the memory in the most efficient way. So if you're solving Poisson's equation, there are actually functions which distributes the memory according to the type of boundary conditions which would be useful for that type of problem. So we often deal with two different types of parallelism. So task parallelism is the one which we will deal with. So that means that the work of a global problem is split into a number of independent tasks and which don't need to synchronize. So there is no, in our case, when you say rarely, it's actually zero need to synchronize. So you will simply just collect the data at the end of the calculation. And it's normally a paradigm which is a little bit limited, but for us, it's just perfect. And we can parallelize in a very easy way the Monte Carlo calculations. So there's not a big hassle. We don't need to think much, actually, in order to parallelize. And then you have data parallelism, which is more the difficult thing. And these libraries like OpenMP, MPI, etc., they actually tailored to the communication between different processes. So message passing is actually one of the most common parallelization paradigms. And the other thing which I wanted to say a little bit of is vectorization, which is a speed up which we can gain without almost doing anything except changing the compiler flag. So I normally recommend doing this irrespective of what you do. And the vectorization means simply, now if you look at this type of operation which you have here, this sum, there are specific parts of a code which can be vectorized and other parts which cannot be vectorized. So if you don't vectorize, this will just optimize. If you just have the 0 flag in your compiler options, the program will execute the program as it stands. So it starts with 0, goes to 1, 2, 3, etc., and just repeats this operation in a sequential manner. Vectorization means that you can run several of these operations in parallel. And that is simply because you use the registers. So there are typical registers which you can have access to. Normally it's a 256-bit, 128 bits. And so the vectorization gives you some type of parallelism when you just apply one type of instruction to many parts of a vector. So the typical ones, your typical instruction could be something operating 128-bit operand. So you can have 4 floats or integers, which if you have integers of length 32 bits, or you can have 2 doubles. The typical other types of registers you have will be twice this, 256 or even more. So if you look at this simple example here, this is a type of scalar operations. So if the code is not vectorized and you have a 128-bit register to store 32 bits floating point number, it means that 3 times 32 bits are not being used in the register. You're just using one of them. So that means that when you run the operations here and you start thinking of the run, so you have one load for B, and then you add CI and BI to give AOI, and then you have to store AI in an address. So the number of elements which you can act upon if you have a 128-bit register is actually 4 elements if you run with a float or an integer of length 32. So that means that what you can do then is to run these 4 operations in parallel if you vectorize. If you don't vectorize, you just run the first operation which you have here. That means only that one. And then the 3 other ones are just left empty and nothing happens. So when you put back the pointer to I equal to 1, then you repeat this step, and then this goes through till you have done it n times. So you see now that if you vectorize your code with one of these flags like O2 or O3, then the compiler will actually allow you to run these operations in parallel. So that means that you can, if you don't have any exit statements and so on, you can actually gain a speed up of a factor 3 to 4 here, or 3 typically. So this is something which you wouldn't disdain. It's actually, you get it for free without doing anything. So think of these compiler flags when you're running the production code. So typically, when you have the number of operations when you're vectorized, is you have one vector load in that address, you have one load for that one, and then you would still repeat these operations, but now you actually perform 4 of these in the same time. Now, there is a code here which you can access, and where I actually run some simple calculations where I perform these operations. And you can see this is a standard C++ code here. where I'm just setting up a simple function in terms of sines and cosines here. And then I'm just performing an addition of these two functions. And I'm doing that pretty many times. And then I calculate the norm 2 of that function. I do my clocking, etc., and figure out how much speed up I get. And there are different ways you can compile this. If you're on a Mac, you can, there's a compiler flag with no vectorization. So this is -0 here. You don't do anything. You can vectorize with this one. And you can also look at different compiler options on how you vectorize loops here. So the speed up depends obviously on the size of the vectors. So what I did was to actually run with 10 to the 7th elements. And this was run on an earlier Mac, which I had 1 or 2 years ago. And this is also the processes of which I had. And you can see now that for the vectorized calculation, I actually spent, so this is the norm computation. So this is the one which was vectorized, and this is the one which was not vectorized. So there is a kind of speed up of a factor of non-negligible factor here. And similarly, you can see here as well, this is the result which I get when I vectorize and not vectorize. Now, when you get a much, much larger element here, a number of elements, what happens then is that you then end up with moving out of the random access memory. So you're then going into the slower type of memory. I'm coming back to that. So when your matrix or your vector becomes very long, what happens then is that you often end up having to go out of random access memory or fast memory, and then you would typically have to access other types of memory which are slower, and that can slow down your performance. So you may not get the kind of speed up if you think that you get a speed up if you increase this with a factor of 10, 1 order magnitude. You would expect then that you would spend 1 order magnitude more time, but you reach a certain wall when you then cannot access the matrix elements or the vector elements in the random or the fast memory. So I will just come back to some of these things. So these are just examples of types of the problems. One thing to think of is that when you are setting up for vectorization, not all loops can be vectorized. So one of the essential requirements is that the endpoint has to be known, because else the compiler doesn't know how to vectorize properly. So another thing which you should avoid are if statements or break statements like this, because the compiler doesn't know when it should break. And what it will then give you as a flag when you compile your program is that I cannot compile, I cannot vectorize or optimize this part of the code. So having loops like this, where you don't know exactly when it breaks, is something which the compiler would not be able to deal with, and then it will simply refuse to vectorize that part of the code. So when you're writing, and this is particular for Monte Carlo calculations, when you're looking at your most expensive loops, what you should think of then is to avoid having if statements or even call to functions inside that loop. Now, one thing you can parallelize are the so-called implicit functions of a programming language, because these are often written in a highly efficient way. So they are ready-made for vectorization. So if you call cosine or exponentials, etc., these are function calls which are highly vectorized. So they are ready-made for you to use with vectorization. But you have an if statement like that, this will actually spoil your vectorization. So typically, as I said, as a switch statement, normally hinders vectorization since different statements cannot branch properly. This code here can actually be vectorized since the if statement is implemented as what is called a masked assignment. So this is a code which the compiler would actually vectorize. You have One other thing to think of is that when you vectorize, it's the inner loop which is vectorized. Because vectorization acts, as it says, on vectors, right? So you have to be a little bit careful on how you deal with, let's say, matrix additions or matrix multiplications when you're dealing with vectorization. And then, as I said, calls to programmer-defined functions can often ruin vectorization, whereas the calls to intrinsic functions, they allow since they are normally efficiently vectorized. Another thing you should think of for you who are C++ programmers, I guess you're familiar with inline functions. Is any one of you has never used an inline function? So inline functions can normally be vectorized because what happens then is that you simply paste you define a function which you use many, many times. So instead of calling that function, you paste all the statements in. When you run the code, what the compiler does is that it simply takes that function and pastes it in all the places where it's called. So inline functions are very efficient and they can be easily vectorized. So these are kind of strategies I want you to think a little bit about when you're setting up your calculations. There's another thing which is also useful to think of, and that is if you have data dependencies. And data dependencies ruin vectorization. So if you look at this line here, where you have a dependence on a previous result, because when you're vectorizing, if you go back, if we now look at the basic operation, if you now have a 128-bit register, so let's just go back to this one. If you look at these operations here, there are no dependents in the B's from the previous values. This is just a lookup in a table with no dependence on a previous value. If you, however, have an algorithm like the one which you saw here, this one, you see now that you're looking up an element from a previous calculation. And that will actually use, and you see that immediately here, because in this case, you cannot run these operations in parallel. No, you cannot vectorize this one because there's an explicit dependence on a previous result. So this would be an example of a code which cannot be vectorized. So these are things to think of. They're just small things, but these are things which, if you think properly about them, they can actually speed up your code. This applies to any programming language. This is not limited to, let's say, C++ or Fortran and vectorization there. Yeah? Yeah, that's correct. So these are just things to think of. And another thing to also think of is something which is called memory stride. Are you familiar with that concept of memory stride? So memory stride, if you think now of a matrix addition in C++, so in C++, you run the calculations by rows and then columns. So that means that if you look at here, your outer loop starts with the row number, and then you run through the columns. So that means that if you're setting up a table with your matrices, if you think of a matrix element, so you would have matrix elements A11, A12, A13, and this goes up to A1n. And then you have A1, 2, not 2, 1, A31, and down all the way to AN1, etc. So when you do this in a row-based way, it means that the way the matrix is stored in memory means that you move from A1 and then you fetch this element. So you have a row ordered storage of the matrix. Now, if you had interchanged these variables, I and j here, that means that when you were looking at the A12, you would have to jump down here in memory. So the matrix elements are stored subsequently from A11, A12, A13, and so on. And then you move down to the next row, and then the next row, etc., etc. So if you're looking after a matrix element here, then you would have to jump in memory down here. So these jumps in memory, if you interchange the indices, this can actually lead to a slowdown of your program. So just think of that. Look at your matrices. If you're dealing with matrix multiplications or matrix additions, this is something which you need to consider. This is also one of the bottlenecks if you link a C++ program with, let's say, a Fortran program. So normally you have wrappers which do this for you with no pain. But Fortran code stores the matrix elements the opposite way. Fortran orders the matrix elements in a column-based way. So if you're calling a Fortran function without taking that into consideration, it may return the wrong matrix elements for you. So it's pretty common to have libraries which are written in Fortran. So libraries like LAPACK are actually written in Fortran. And the C++ variant is nothing but a wrapper code to the Fortran libraries. And that wrapper code does this for you automatically. So these are some kind of small things to think of. Actually, Python is, NumPy is just a wrapper to LAPACK and many of the others libraries. And if you look at a software like MATLAB, they just took all these functions and just put them in written Fortran and made wrappers and nice interfaces to the codes, right? So this is a technicality, but it can actually, if you just call a Fortran program without thinking from your C++ code, it can give you wrong results. Oops, I went quite over time here. So we will just use the last part here to say a little bit more about this optimization piece. And I wanted to say something about memory management, because that's also something which is useful to look at. So if you think of memory, you would typically have a cache memory, and this is normally faster, but consumes more space and power. And it's normally assumed to be faster than main memory. And typically registers, they contain only the data you work on at that specific model. So modern CPUs perform most of all operations only on data and registers. And then we have multiple cache memories. So you typically have L1 cache, which is the fastest one, L2, L3. And you will typically see if you have huge vectors or huge matrices, then memory will be distributed in these different slots here. And some of them can be accessed fast, and some of them can be a little bit slower to access. So most of the, as I say, communication is carried out in chunks, and you have blocks of bytes of data that move together. And then in the memory hierarchy, you move between memory and cache and between different levels of cache. And these are just some technicalities. So when you measure performance, here's a typical example, which can be useful when you measure performance. So one thing which is worth thinking of then is that the times you're setting up, they are not necessarily accurate, or this clock which you see. So when I'm performing a measurement, so I could typically define a clock start and finish. And the problems are that the times are not infinitely accurate. So all these clocks have a given granularity. That's the minimum time they can measure. So when you're testing your program for time, you should test it so that you actually have many examples. For for vectors, you need many elements, because then you could actually get a wrong measurement of time if you just run it for some few hundred or few thousand matrix elements. And so you should ensure that it is long enough. You should also know the granularity of your clock. And it could actually be the error in the measurement could be given by the granularity of the clock. Then you also have something which is called a cold start. So when a code is executed, when you're clocking your program, you have system time and you have runtime. And you have to be a little bit careful when you look at this, because sometimes the code may still be on disk and it's not even read into memory. So when you're clocking, then it would also include that time. So data may be slow in memory rather than fast. Multiple tests are normally necessary to ensure that cold start effects are not present. And then you also need to ensure that the intended part of the memory hierarchy is actually accessed. So you also have problems with smart compilers. If the result of a computation is not used, the compiler may eliminate the code. Performance will then look fantastic. And even worse, they eliminate some of the code so the performance looks plausible. And also you should ensure that the results which are there are actually used. So sometimes if things are not used, it actually may, the compiler, when you make some smart compiler flags, may actually eliminate that part of the code. When you're clocking, this is a thing to think of. If you're looking at the specs of a specific compiler and a specific algorithm you have implemented, you should run this many times. So think of you clocking your program as an experiment. And you're running that on a piece of hardware, which is an experimental equipment. So every time when I run my code on my laptop, it gives me slightly different times. Sometimes the code may not be read properly into memory. There may be these cold starts, as I mentioned. And then there may be other things which slow down the code, like memory reads and memory writes. And that may not be the time you do for memory read and memory write, may not be the same every time you read it, because suddenly there is your fancy browser, which is now accessing some nice movies, which you would prefer to watch instead of listening to the lectures. And that takes a huge chunk of memory. And if you're running a code and you have your browser running, that may actually slow down the way you access things in memory. So depending on how your system is set up and what are the background jobs, you can have different performances every time you make a measurement. So these are just things to think of when you're looking at the performance of your code. There are many small kind of details here. So there is an algorithm here which I wanted to mention a little bit, and this is actually for solving. Some of you may have encountered this algorithm before. This is for solving a set of linear algebra problems where the matrix is three-diagonal and where typically the matrix elements change along these the diagonal axis and the two sub-diagonal axes. So this algorithm is an algorithm where you have specific steps, but every time you do this type of steps, you will see now that here you have one multiplication and one division and one subtraction. So that would be free floating point operations. And you can speed up this. This is actually an algorithm which you can speed up by having, so I should have it down here. If you only look at the number of divisions and multiplications, etc., that is just one part of the time your program spends on implementing the algorithm. But in this case, you would actually have a lot of memory reads and a lot of memory writes. And this can change depending on what kind of programs are running in the background and how you access memory. So these are small things to think of when you are looking at the timing of your code. So I'm not going to go through everything here. There's also an example here on the transpose of a matrix and some matrix multiplications and examples which you with timing. So you will actually find access to all these codes. And if you wish to play around, if you click on the links here, you can actually get access to these codes. And these, for those of you who write programs in C++, these can be useful to study as examples of timing. And I've kept these programs as simple. They are as simple as possible. There are no objects which can often slow down performance. So this is just a straightforward C++ code, which is actually almost like a C-like program, except that we are using different ways to allocate memory compared with C. So these are just examples. Now, when you look at speedup, the speedup measures the ratio of performance between two objects, and versions of same code with different number of processors. That's typically the standard situation. And then you can compare serial, vector versions, parallelized versions. You can even try different programming languages if you have, if you want to. So some people do that when you develop codes. And there is always this kind of tension between people who write in C++ and Fortran, which one is the most efficient one on high performance computing facilities. And until recently, before you had just-in-time compilation and efficient libraries like JAX, I mean, Python codes tended to be much, much slower than C++ and Fortran, but there's been quite some progress in the last years. So often it's actually not so bad to compare different programming languages on a simpler problem, and just to see which one is the most efficient for that specific problem. Because in general, C++ and Fortran programs tend to give basically the same timing. There's not that much difference. There used to be, but there's not much more. So the key is normally to choose the correct baseline for comparison. For these kind of examples where we have serial versus vectorization, when you use this compiler provided vectorization, the baseline is simple, the same code with vectorization turned off. When you parallelize, it can often be much more difficult. So in parallelization, we often discuss speed up in terms of the time on one processor divided by the time using P processors. One thing you will see in Monte Carlo calculations is that you will simply get a speed up of 100%. That means that since the jobs don't require any communications, except when you start it and when you collect the data, there is essentially no memory synchronization during the runs. That means that you splitting the job on different processes means that if everyone runs at the same speed and nothing else happens, if somebody is running some browsers which suck a lot of CPU cycles, that may slow down things on one of the units. But if you run this on a high performance computing facilities, these job nodes, they are just dedicated job nodes. So you can have login nodes where you compile and test, do simple tests, but the nodes which you run on for a specific production run, they are normally nodes which just do only the instructions which they are supposed to do. So that means that normally for a Monte Carlo code, you would actually get a speed up which is 100%. So if you run with 100 nodes, you will get a speed up of 100, typically. And that's these are typical definitions on how you would measure. So if you're running on with a lot of synchronization and so on, then the speed up on P process can be greater than P if memory usage is optimal. I'm just going to leave out some of these things here. You can actually look up these things yourself here. But the general expression is that if you look at the speed up, when we have a typical Monte Carlo job, if you look at this W, which is a time on one process, a fraction F of that work will take time, this time on the P processes. And in the Monte Carlo calculation, what you are going to see is that you will essentially have something which gets pretty close to a speed up of 100%. This is often the case with Monte Carlo calculation because there is no time spent on memory synchronization. So how much is parallelizable? This is actually the big question. In Monte Carlo calculation, as I said, basically your whole machinery is parallelizable. So you would typically run different jobs on different nodes and simply collect the data at the end. That's basically what you end up doing. So I wanted to, I'm not going to repeat everything here, which we, because we discussed a little bit on that last time. So MPI is one of the possibilities, and we mentioned how you can install it. So there's the Open MPI website. If you don't have it on your laptops, I would recommend installing it. And last time we actually went through the basics of a MPI setup. So as you see here, when you run your code, these are the instructions which you would give, MPI exec, and this tells you that there are 8 nodes, and this will be the name of your program. You need to compile it so that the synchronization and the communication between nodes can be set up properly. So if we go down and look a little bit after having installed it, I wanted to just bring up this program which we discussed last time on integration. And Monte Carlo, variational Monte Carlos is essentially a multidimensional integration. So what we are doing then is in principle to calculate an integral. So what we can do then is to, since we run this stochastically, we can actually let every process run its own calculation of the integrals, produce a finite value, and that would be one measurement. And then we would run this, let's say 100 times, and then the total average would be the average of all these 100 measurements. So in that case, the thing I only wanted to repeat to you is that if you want to use MPI for the parallelization of the Monte Carlo code, you would have to have in the beginning the MPI initializations, where you then simply tell, actually read in from the command line, the number of arguments here, which is then translated into the number of processes. And then you read in the command, the program name. So this MPI com world is actually a common variable for all the processes, and that holds information about the number of processes which participate and the rank of the process. Normally, the main node is given rank 0. And then you can do in this case, we're actually splitting everything into sub-calculations, smaller parts which we calculate. And then the smaller parts are then calculated by themselves here. So we have a local integration limit, start and end. We have a local number of integration points. And then we simply call the trapezoidal rule here, or your Monte Carlo sampling, just the metropolis sampling, which you're doing. And that produces an output, which is the local sum here. In your case, it will be the energy. It could be the energy squared, which it returns. And then you would then calculate the total sum, which now takes the local sums. And this is this MPI reduce function, which you have here. And then you would have a total sum. You have only one variable. You can have arrays of variables if you want. So then you would have to specify the dimensionality. You specify that this is a double. And then there is an MPI operation, which is called sum. So that means that you sum the local contributions, and that sums it up to the total sum. And it's only the first process which gets the total sum. So you can change this in MPI to MPI all reduce. With all reduce, it means that all the processes will have also the total sum. But for a typical variational Monte Carlo calculation, which is a main process collecting from all the other ones, you are pretty, how to say, set if you just use MPI reduce. So that collects the local sums, add to the total sum, because we have this MPI sum command. Then you can calculate the time which you're spending. And then if rank is equal 0, which is the same as you specified here. So every process is running a copy of your program. So then, since they synchronize, then you can say, okay, rank 0, that's the one which writes the final result. Because if you let all of them write, all of them will try to write and compete which one writes first. You can order that. We have commands like MPI barrier and so on, but for us, this is not necessary. So the only thing we need, if you use MPI, are these three statements to initialize and tell all the processes which rank they have and how many we are. And then you do the MPI reduce, the local calculation. And then at the finally, you need to finalize everything. So you need only 5 additional lines here. Essentially, that's what you end up to use. If you, on the other hand, want to use OpenMP, so there are some more dissections here. Actually, here you will also find a quantum dot program, the one which we have been using in the lectures in Python, and how you could do the Monte Carlo calculation or sampling here. And you will see now that in this specific case, we declare the different functions. These are just declarations. And then if we go to the main program, so these are lots of local programs, but then we would have the main program, which you will find below here. You will find the start of everything, and where we just initialize MPI, etc., etc. So I'm not going to go through that one because this is a lengthier program. It just contains everything which you would need. So OpenMP is tailored to shared memory, and it's perhaps even simpler to use than MPI. I mean, you need less commands here. So the first thing you need to do is actually to have this statement here, openmp.h, and then every compiler directive is now given by something like this hashtag and pragma and OMP. And you would typically compile with fopenmp and the name of the code. And the typical directives which you have is something like a pragma, OMP, and then some specific commands. So let's just see at a specific function which you would have here. If you want to define a parallel region, you will simply set up pragma OMP parallel. You have variables which are default variables, something which are public and private. So if you take the hello world program here, you would now simply define pragma OMP parallel, and then this finds the thread number, and then this writes out in parallel for the different processes, depending on how many threads you've started and how many threads you have access to. And similarly, you can actually set up a barrier so it prints out in an ordered way. There are different variants, but I just wanted to show you some of the typical examples which we would end up with. So let me just look at a typical parallel computation. So if you want to run this code here in parallel, you will simply have pragma OMP parallel, and then you indicate that this for loop here is run in parallel. And then depending on how many threads you have available, you would then have the effective initializations and parallelization here. So remember that this works on a shared memory. You can schedule loop computations. If you look at a typical example for a loop computation here, you can define a region here, which is parallel. You have some variables which are shared and some variables which are private to that specific process. So the shared ones are variables which are shared by all the threads. And then you can schedule this to be dynamic. And then you can simply set up the operation here. So A, B, and C are shared, whereas this variable I is now split by the compiler. It figures out which I a given thread should use. And that's why this is set as private here. So there are many ways of doing this. I have some examples below here on a matrix-matrix multiplication. So, or just as an inner product. This would be another example if you're doing the inner product of these two vectors. You allocate, initialize the arrays, and then you have a pragma OMP parallel, and then you have a for loop. You have default shared, and then private I. And that is a way to split the sum so that the different threads know exactly where they start and where they end, whereas A and B are shared by all the processes. Okay, You can look up many of these examples. It's actually not that difficult. There is a full example on a matrix-matrix multiplication, which would not be that different from what you would have in the final project. So I'm going to stop here.